hear me? Can you hear me? Okay, good. So, good morning, everyone. I want to thank the organizer for giving me the opportunity to present our work here. I'm actually talking for my team, which is composed of Olivier, Louis Captain, a postdoc in my group, and Lisa Posani, a student in my group. So this is our first CASP experience. So I want to also put it a bit in context. This is the email that we and many other people in the MD community received at the beginning of June from the assessors of this target. And so I will not describe it because it has been described very well in the previous presentation, but to give some context, so in our group, we use a lot molecular dynamics, so we are experts in that. We have also some experience with modeling RNA magnesium ion interactions, and we have a strong interest, and we are now working on the integration of MD with cryo-EM data to study flexible RNA molecules. So, and finally, we have just funded grant to work exactly on this topic. Like, really, is the goal of this grant is to use cryo-EM data and MD to identify where magnesium binds to RNA. So this is really the challenge for us. But if there are Italians here, you know that setting a deadline in August the 6th is not optimal. But anyway, we took the challenge and we tried to do it. So this is the system. Again, it's not, the details were explained before. The most important thing that I want to point out is, so we did MD, so which force field we use. We use the standard Amber force field, the standard water model, type 3P, and the non-standard or relatively new parameters for magnesium. These micro magnesium parameters from the group of Nadine Schwirtz, that were basically fine-tuned to have the correct affinity between magnesium and phosphates, so that the fraction of bound magnesium should be right, but also the correct kinetics. So the kinetic of water exchange is slow, it's on the microsecond timescale, and the kinetics of binding with phosphate is even slower, as it should be in reality. So this is actually difficult to use in MD, because it means that if we can run simulations of a few hundred nanoseconds, maybe few microseconds, we will basically see nothing. So we had to tackle this using enhanced sampling method, and actually, luckily, we have quite some experience in this. So it's quite technical, and you find all the details in the abstract, but I want to give you an idea of what we did. So we basically designed ad hoc bias potentials to make our magnesium more happy to bind quickly to phosphates, basically acting on the distance from each magnesium and the closest phosphate oxygen, and also with the coordination with water. So to make sure that the water coordination can go from 6 to 5, say. In this way, we change, however, the potential. So we kind of cheat, and to recover the original results, what we use is a replica exchange procedure, where we basically, for this system, we use like 5 replicas with the normal simulation setup, that's a normal force field, and then additional 11 replicas with the stronger and stronger of this correction. So, and this can be shown to be correct and give the correct statistics in the lowest replicas, basically. Okay, good. So what you see on the left is a movie taken at the beginning of the simulation. What you see on the right is after 160 nanoseconds per replica. It was roughly 10 days of simulation. And actually, when we received the email, we were still working on the method. So we really ran this in the last 10 days, so beginning of August, just before the submission. So one thing that I want to mention that I think it's important is that we had to adjust the number of magnesium during the simulation or in preliminary steps, let's say, to match the concentration in the bulk, because RNA is going to suck in a lot of magnesium. So this is very important when you do simulations. You don't have to just put the correct number of ions in the box based on how much water there is, but you have to adjust it, because at some point in the system we reach equilibrium. You see it's equilibrated, and in some way we can have correct concentration, correct matching with the experiment, the concentration of both magnesium and sodium in this setup. Okay, good. So how did we try to self-assess these results? So actually with MD, you have typically 2 independent source of errors. One is a statistical error, which leads to low precision. So it's a horizontal axis here, let's say. And this is typical when you do short simulations. And I think that by using enhanced sampling, we managed to have quite significantly more samples, independent samples. And this is kind of testable also with the information that we have, because, and let's say, check how the result depends on the simulation length, and we can check if our simulations look like converge or not. It's more difficult to do the vertical check, which is a check for accuracy, but this is actually what this target was designed for. So to compare with experiment. And this is very useful for us because it could give us the necessary information to also like improve the force field, for instance. The point is, are experimental data sensitive enough to tell us if the ion placement that we did is correct or not? So we tried to do experimentally before actually we received the data last week, some test of our results. So what we did, basically, we took all the magnesium ions that are in the published PDB, the one that everyone has access to, and we tried to remove them one by one or replace them with water, and looking if the cross correlation with experiment was increasing or decreasing. And you see that opt is magnesium actually. Whenever we replace magnesium with something else, the agreement with experiment becomes worse. So that means that for this structure, we believe that the magnesium ions were placed correctly by the experimentalists. And then we do the same analysis for the new sites, those that we predict from our simulation, with a significant occupation, because we have also transiently occupied sites. And we see something which is not as good, but still it's promising, because in most of the cases, the prediction is at least compatible with the experiment. And in some cases, it's also in agreement with the experiment, so that the experiment confirms the prediction. So I think this is sort of good. So what went well? So I think that the strategy for enhanced sampling, even if it was designed really, really quickly, worked well. We managed to sample very quickly and to identify very quickly a lot of bound states, and in a relatively short simulation time. And as I said, this was really preliminary. We further work on the method. And so what we used for the challenge was a method where we can only see magnesium, which is basically penta-coordinated with water and coordinated with one phosphate. But now we have a way to study more deeply buried ions, and we want to test this on the big system and other systems as well. So what went wrong? So I think the validation is challenging. I'm happy that we resulted first, at least in some of the scoring. But I think there is so I also want to try to be able to reproduce it myself and see how robust it is. And there is one very tricky thing that RNA can move in the simulation. So one has to be able to disentangle what's wrong with RNA dynamics and what's wrong with the water and ion dynamics, which is not trivial. And what's next? So I would like to run this protocol using multiple systems where we have access to these very good high-resolution cryo-EM maps. I don't know how many we have, but I know that Riju promised to make one per week or so. If so, this would be super useful for us. And also, I would like to run this systematically on different magnesium and water force fields to see which one is most accurate. And this would be very useful to propose better parameters to the community. And finally, one thing that I discussed yesterday that I didn't think about, actually, it was told to me by Xiji Chen, is once we have, if at some point we have reliable magnesium ensembles, maybe they could be used to train deep learning methods, because as many people know, many of the magnesium deposited in the PDB are not correct. So maybe it would be better to have ensembles which are generated in this way to train deep learning method. And then that's it. Thank you for your attention.